everybody. Welcome to the Synthetic Intelligence Forum. My name is Vic, and I'm the founder and the host of the forum. Today, I'm very happy to be joined by Professor Warren Powell. Professor Powell is a Professor Emeritus at Princeton University, and today he's going to talk to us about sequential decision analytics, stochastic optimization, and reinforcement learning. Thank you so much for joining us, Professor Powell. It's an absolute pleasure and privilege and honor for us to host you in the Synthetic Intelligence Forum. And without further ado, I'd like to say the floor is yours. So take us away.
Vic, thanks very much. And I'm really pleased to be speaking to the Synthetic Intelligence Forum. I'm the Chief Innovation Officer of Optimal Dynamics, but I'm also Professor Emeritus at Princeton University, where I taught for 39 years. And what I did at Princeton largely was focus on a wide range of problems. I started off with trucking, rail, air cargo, moved into energy, health, did some work in materials science there in the lower left-hand corner, robotics, e-commerce. And by the way, all of these are complex sequential decision problems where we have to make decisions under uncertainty. So these problems arise in virtually any aspect of human processes. And so no matter what field that you come from, I'm going to claim that you have to make decisions and you have to deal with uncertainties. Now, when we're making decisions, we want to achieve something. So we're going to have various goals and objectives. Maybe we want to maximize profits or just reduce costs. But maybe I want to increase the strength of a material or reduce my carbon footprint. I may want to reduce illness or maximize productivity. So we have all of these metrics. And at some point, somebody's going to say, well, how do we perform better? Well, the answer is you have to make better decisions. Now, I'm going to come back to that, but I'm going to briefly make the point. In order to perform better, you have to make better decisions, which means you better be able to list what decisions that you're making. Now, once you've got the decisions identified, how do you make better decisions? And I know somebody's going to come rolling in and says, oh, we need to use artificial intelligence. So brief background, because a lot of people use AI and what they really mean is machine learning or something like that. In the 1960s and 70s, AI was rules. You know, if you're eating red meat, then drink red wine. Or if you have a male patient over 60s with high blood sugar, then use this treatment. In the 1990s, optimization came rolling in, and this was a very powerful tool, and we could optimize airlines. But when we tried to take it to other problems that had uncertainties like supply chains, things failed. In the early 2000s, artificial intelligence became equivalent to machine learning, and we see this outpouring of work in neural networks that's ongoing today. Now, roughly around 2015 is when the community working on reinforcement learning start to emerge and become highly visible. These are the tools that people use to play computer chess or computer Go, and suddenly we had computers that were outperforming top experts. So what's the next wave in the 2020s? I claim it's going to be sequential decision analytics, which is a stepping stone from reinforcement learning. So I'm going to start off by talking about the 5 layers of intelligence. The 5 layers of intelligence, at the very top layer is making decisions, and that's the layer that I want to get to. But you have to remember that there's these bottom layers. The bottom 3, we start with information acquisition. What's the state of the world? What's climate? What's the state of the patient? What's the ocean temperature? You have communication and storage, massive improvements in our ability to store and transmit information. Then you get the good old transactions and execution, which usually means a room full of computers with people at it making decisions. And whether you're in a shop floor or a dispatch center or you're a doctor in a hospital, it's a human looking at data and making decisions. Now, the 4th layer, let's briefly pause at that learning, because this is what's getting so much attention today. So the learning layer comes in 4 categories. Pattern matching, is that a picture of a flower? Classification, I have a customer logged into the internet. Should I offer him eyeglasses as a product to buy? Inference, how will an increase in price affect market demand? And what's the condition of a piece of equipment? How will a patient respond to a particular drug? And then there's good old-fashioned prediction. Here's a bunch of history, and I want to predict the future. Now, anytime you do machine learning, you're going to be pulling from one of 3 overlapping classes of functions. What we call lookup tables, if the patient is male, then do, parametric models and non-parametric models. And somebody may say, well, wait a minute, where's neural networks? Well, there's neural networks. It sort of falls in the overlap between parametric and non-parametric. So let's imagine, let's look at machine learning as an optimization problem and imagine we're trying to come up with a function. Let's take the setting where I'm trying to predict demand as a function of price. and I have some data, and somebody comes rolling in and says, oh, I think it's a line. And I'll say, oh, okay, if that's what you think it is, let's use the data to fit the best line. Now, somebody else is going to come in and say, no, this has to be some sort of a nonlinear S-curve type of function. And I'll say, fine, let's fit the best we can given the data. Now, today, somebody's going to come rolling in and go, oh, well, of course, you have to fit that with a neural network. I'm going to urge a word of caution, make sure, because neural networks have a tendency to overfit data when there's noise. Either way, you're going to have these three families of functions. And what you're going to do is you're going to have to choose from among the family. Often this is done by a human. And then a computer will say, oh, here's this bunch of tunable parameters. Let's use your training data set in order to fit those parameters. Now, let's pause just a little bit. I want to have a word of caution about neural networks. Here we're observing profit as a function of how much product I put out. And I might put out a certain amount of product and observe profits. And the profits could be high if I have very high demand in sales, or it could be much lower if I don't have as much. But on average, what you're going to get if I fit it with a neural network is that squiggly line, but the red line is the true function. And I know mathematically that this is going to be a smooth concave function, but the neural net doesn't know that, and I get that wiggly function. Here's another one where I have demand as a function of price, and it's that black line, and the higher the price, the lower demand. But if I work with actual observations, which is the red dots, and then fit a deep neural network to that, I get the squiggly green line, because the deep neural network doesn't know that, well, of course, the higher the price, the lower the demand. So I just want to offer that word of caution, because a lot of people think you can do anything with a neural network. But let's get to my favorite topic, which is decisions. Once again, we've got all these people trying to make decisions. Now, I think the 1990s, we thought these images looked really high-tech and fancy because you had computers everywhere, and this was great. Today, it's more like a Model T assembly line in the early 1900s. And we have to remember that in the early 1900s, this was a huge breakthrough. It transformed society. But today we look at it and go, okay, that's kind of old school. Here's what we'd really like to do. We'd like to have like a Tesla factory with all the robots building the cars. So we would like to automate the process of making decisions. Now, let's come back to this set of applications that I worked on. And in all of these applications, there's decisions that we're making. So here is an example of various decisions. Every one of these boxes is a choice where I have to make a choice, and I want to make the best choice. So I have to make these decisions, and I'd like to perform as best I can. Now, decisions come in three broad flavors: decisions that act on physical resources, inventories, dispatching drivers, scheduling nurses, and energy generators; financial decisions, moving money around, signing insurance contracts, managing investments, or hedging. And then there's informational decisions, where the decision is to move information around. This could be marketing and advertising, could be running experiments in a lab or a field. You could be testing drugs. Now, time frames, you can span all the way from strategic planning, where to source parts, how much production capacity to have; tactical planning, where you make a decision now that impacts the future; and the real-time execution decisions. The strategic planning decisions are far enough out. I don't care about the state of the system now. The tactical planning is a decision now that impacts the future, but it does depend on the state of the system now. Real-time execution acts on the state of the system now. And these are the real-time things of dispatching drivers and scheduling machines. Now, anybody can be making these decisions. It can be the C-suite, it can be middle management, it can be field operations. So I'm not drawing any boundaries on what types of decisions that are being made. Now, one of the most powerful tools is something known as deterministic optimization. Shortest paths, when we're trying to find the best path to a network, is a nice example. This is a fairly simple optimization problem. Or maybe I have a big supply chain. I want to optimize where all the facilities go. What we're going to do is use tools of math programming. That bit of mathematics in the middle, not everybody's familiar with that, but many people are. There's a whole lot of people out there with training in this mathematics, and this same mathematics is used all around the world, and people who learn this can go out to a complex problem like an airline, collect data, put it into the software, and out comes an airline schedule. So even if you're not familiar with this mathematics, you can hire people who do know about it. This type of mathematics is a very common language. There's many books that teach it. They all speak the same notational language because of this one book by George Dantzig from the 1950s, because he invented the algorithm for solving this problem. And that's what made this bit of mathematics useful. Now, let's go back to my problem. So we have all of these applications. Behind every one of these things are the various decisions, and we saw that earlier. But after I make a decision, new information arrives. And this information I didn't know when I made the decision. So I have to make my decisions under the uncertainty of what might happen in the future. And of course, all this information is relevant to how well I perform. So these are all sequential decision problems. And I'm going to say most settings are sequential decision problems. You make decisions and new information arrives. And then you make another decision and more information arrives. Information that arrives after a decision is made is not known when the decision is made, which means that we have to do decision making under uncertainty. One example is inventory management, where we place an order that might arrive now or it might arrive days or months into the future, after which I observe the demands for the product, and then I make more inventory decisions, and then I observe more demands, and so on and so forth. Classic inventory problem. My company, Optimal Dynamics, dispatches drivers to loads. So the circles are drivers and the squares are loads, and I'm assigning drivers to loads, and shippers are calling loads in over time. And I have to make decisions dynamically as these new demands are arriving. Now, maybe I'm in health and I have to test out new vaccines, and I have to decide what type of vaccine, what dosage, what type of people, and then I observe the response to the population. And of course, if you work in finance, you've got all this buying, selling, and trading with the dynamically changing prices in the marketplace. So let's take a very simple problem of an asset that I can buy, sell, or hold. Very simple, after which the price goes up, down, or stays the same. Now, this is a really simple problem. As I track all the different trajectories in the future, it gets really complicated very quickly. So this is a toy problem. So think about taking this type of visualization to any of those real world problems. So let's address the problem of modeling a sequential decision problem. If you have a real world application and you want to use the computer to help solve it, you've got to build a mathematical model. Now, all the people doing deterministic optimization all know how to do a mathematical model. They're all trained in this. They're trained in basically the same mathematics. They speak the same language. They all use the same software. Same is true with machine learning. But when you go to the world of sequential decision problems, now we're in trouble. We don't have a standard framework. I like to call this the jungle of stochastic optimization. Every one of these terms is a completely different field. Behind each field is a book, maybe a whole series of books and thousands of papers. You can get a PhD in any one of these topics and spend years of your life. Some people spend an entire career working in the communities of any one of these books. So I'm going to show you how to model a sequential decision problem. We start with the state variable. The state variable is nothing more than what we know or believe, because I may have things that I don't know perfectly. Then I make a decision, and so we saw illustration of decisions, and then new information arrives after I make the decision. State, decision, information. Each time you make a decision, you receive a contribution or incur a cost, some performance metric. Now, decisions are going to be made with a method that we're going to call a policy. And I'm going to make up this function, like if my decision is little x, I'm going to have a function capital X superscript pi. And for now, we're just going to give it a label, and we're going to design it later. And this is a big change from those other books, because virtually all of those other books, they come in with a particular way of making decisions. I use what I call a model first, then solve strategy. We'll design the policy later. Now, after you make a decision, we have a function called a transition function that says, tell me the state, tell me what you know, tell me the decision, tell me the new information that arrives after you make a decision, and I'll give you the updated state variable. And finally, what I want to do is I have the problem of coming up with the best policy. And I'll have to design that later. So this is how we're going to think about a sequential decision problem. I like to write it out this way. There's 5 core components: state variables, that consists of 3 classes of state variables: the physical state, like how much inventory or where are you on the graph or where are the trucks. There's other information like prices and weather. And then you have beliefs. A belief is information about what you believe about a quantity or parameter that you don't know perfectly. We have decision variables. I like X, but other people do A or U. Decisions are determined by a policy. The information I call exogenous information. WT plus 1 is the information after I make decision T. We have the transition function, and then the objective function says, okay, I want to find the best policy that works well on average over time. These 5 elements describe any sequential decision problem. So every single problem in that picture to the right can be modeled with this mathematics. Understand that all of those books I showed you, well, behind those books, it's 15 different books, but there's 8 fundamentally different notational systems. And they just have different ways of modeling. This is a universal modeling framework. Now, a lot of people like to write out problems with an objective function. Now, there can be more than one way of writing an objective function. Maybe I want to maximize expected cumulative costs or contributions. Or maybe I want to run a series of experiments in a lab and I only care about how well I do at the end. That we call the final reward. And sometimes I have to deal with risk. I'm not so much interested in how well I do on average. I'm interested in how badly I might do. Then we have the transition function. Then we have the exogenous information function. Again, this mathematics will replace all 15 of these books. Any of the problems in any of these books can be modeled with this mathematics. And of course, in the objective function, we're always searching over policies. Now, I like to break down the whole modeling as a process into 6 steps, beginning with step 1, where there's no mathematics. I have to get the answers to the following 3 questions. What are your performance metrics? What are your types of decisions? What are your sources of uncertainty? There's a lot of complex problems in supply chains and energy and health where people go, oh my gosh, this problem is so complicated. If I'm going to build a mathematical model, I have to have the answer to those 3 questions. I claim even if you're not going to build a mathematical model, you should have the answers to those 3 questions if you want to think about a problem clearly. Now, if you do want to build a model, you take the answers to those 3 questions as a starting point. Those are an input to fill out the 5 components. After you've got the 5 components, I have to go to the sources of uncertainty and model the uncertainties and model the new information coming in. Then step 4, designing policies. And I'm going to get back to that. Computer model. Now you put it on the computer and you start running your simulations or using things. Sometimes you're going to evaluate policies using a simulator, sometimes in the field. And then step 6, this is where we take our results and go to the field and have an impact on the real world. All right, so let's address this problem of designing policies. I get a lot of questions of, Warren, what do you mean by a policy? A policy is a method that makes a decision using the information in the state variable. Any method. Now, there are many words that basically mean policy. I'm up to about 45 of them for the English language. And all of these words, at least in certain contexts, mean here's what to do in this setting. Now, when I want to design the best policy, now I have to get into the challenge of designing policies. Now, if I'm going to evaluate policies, how do I evaluate policies? There's 3 core strategies. First of all, the academic literature is full of theoretical results, optimality proofs, regret bounds, asymptotic convergence. And the academic literature is full of these results. Generally, you're going to end up using a simulator to simulate things because most problems are too complicated. We can't actually prove things. And then finally, sometimes we can't even run things on the simulator. We actually have to go to the field and see how well they work in the field. Sometimes supported by a simulator, often not. Now, let me build a bridge between machine learning and sequential decisions because it's really neat to see the relationship between machine learning and sequential decisions. In machine learning, we're looking for functions. We refer to the functions as statistical models. And we have to go to these 3 classes of lookup tables, parametric and non-parametric. For sequential decisions, we're also looking for functions. It's just that we call the functions policies, and these are methods for making a decision. In machine learning, we're going to do our fitting with the training data set. That's our big data set. With sequential decisions, we do not use a training data set. We use a model of the physical problem. Okay, so here we see that there are very close parallels between machine learning and sequential decisions. Big difference initially is we don't use a training data set. We just use a model of the physical problem. But now let's get to the issue of how do we search over policies. So it turns out there are two fundamental strategies for creating policies. One I call policy search. This is where I take a family of functions and I say, what's the best function in the family, or the best, if I had to tune the function, the best function within a class that works as best possible over time. And usually I'm doing that with a simulator. The second one is with look-aheads. This is where what I'm going to do is I'm going to take the immediate performance of a decision plus the downstream impact, and I want to optimize over the effect now plus any downstream contributions. Now, each of these two strategies I can divide into two classes, creating what I call the 4 classes of policies. Let's start off with the policy search strategy. So the first of the two classes under policy search is called policy function approximations. These are very simple rules and methods, like ordering inventory. If the inventory goes below a lower amount, I'll call it theta min. You order up to a higher amount called theta max. Finance, buy low, sell high. PFAs are any function, it's analytical, you've got tunable parameters, and you have to tune the parameters so they work as well over time. It can be any lookup table, linear, nonlinear model, neural networks, non-parametric, actually any function that you might use in machine learning. Now, cost function approximations. These are parameterized optimization problems, usually simplified, usually deterministic. If I find the shortest path to a destination, I also have to figure out at what time should I leave. And so let's say my navigation system says it'll take 40 minutes, but there's traffic. So I'll say, okay, I'm going to add in an extra 15 minutes just to be safe. That 15 minutes buffer is a tunable parameter. If I do that over and over again, I'll learn whether the 15 minutes is too much or too little. Maybe I'm scheduling nurses and they work 40 hours a week. I'll plan for using them 32 hours a week because random stuff comes up in emergencies and this is health. Or here's a very popular policy. What product X should I advertise? And let's say I'm Google or Facebook and I want to maximize my ad revenue. What we're going to do is to take the estimated revenue, and it's just an estimate, and it might not be a very good estimate, and maybe I had some bad luck, so it's lower than it should be. So simply taking the product with the highest estimated revenue may not be very good. So what I'm going to also do is I'm also going to figure out the standard deviation, and I'm going to create something. I'm going to take the estimated revenue plus theta times the standard deviation and maximize that. The thing is I have to tune theta. So theta is my tunable parameter, but notice that it's still an optimization problem. I have to find the maximum over all those values. Parametric CFAs are widely used in practice, utterly ignored by the academic community. But this is a very powerful method, especially for more complex problems. Here's a little example in laboratory science. I'm trying to make a material that has the maximum strength. I have to pick the best of 7 catalysts. Testing a catalyst is very expensive. So I have my 7 catalysts, and I have a rough idea how well each will perform, but a lot of uncertainty. Now, what I can do is, let's say I run an experiment for that 7th one, and maybe it outperforms. Well, did I just get lucky? I can use my statistical methods to update my belief, and maybe I have correlated beliefs where trying one catalyst teaches me about the other ones. Now, what I need is a policy. Well, I'm going to do 3 flavors of that policy I just showed you. Each one I'm going to have an estimate mu bar. I'm going to do an argmax over what's in parentheses, and each one of these has a tunable parameter. Okay. Now, what we're doing is that tunable parameter is allowing us to bring in the effect of uncertainty. So if there's more uncertainty, I say, wow, I may have an estimate mu bar, but I have this much uncertainty. So I may say this might be better than expected. Now, one of my favorite is that middle one, interval estimation. I have found it works really well. So let's imagine we put that tunable parameter theta equal to 0. That means I'm evaluating each of these catalysts based on the expected performance. Well, what if I set the theta equal to 2? Now I'm going to evaluate each one based on like the 95th percentile. And now that 7th catalyst would be the one that I would test next. Now, what I can do is I have to tune theta. And what I have to do is I normally will put that in a simulator. Now, the graph down at the lower right there is plotting the opportunity cost. Smaller is better. Now, I'm comparing the IE, the interval estimation policy, against a very sophisticated policy that we developed in my lab called knowledge gradient. And this knowledge gradient is a whole algorithm that you have to code up, and it works really, really well. But it turns out that with interval estimation, if you tune it perfectly, it outperforms knowledge gradient, and it's way simpler to use. Now, knowledge gradient still has certain advantages, but I was blown away when I found that this very simple policy, properly tuned, would outperform the much more complicated policy. Cost function approximations you won't find in the academic literature, but airlines use it every time they optimize schedules and they put in schedule slack. Manufacturers, when they optimize their supply chains, but they put in buffer stocks. Grid operators planning energy for tomorrow will allow extra generation capacity in case one of the power plants breaks down. This is a very standard policy in practice, but it's done in an ad hoc way. If you go to this link, tinyurl.com/CFA policy, there's a whole web page introducing you to cost function approximations. Now, whether you're using PFAs or CFAs, you have tunable parameters. And what you're going to have to do, let's imagine that you have a surface. Now, I don't know what that surface is, but what I can do is maybe pick two values of a value of theta 1 and theta 2. But when I go to observe the surface, I get a noisy observation. And that's what makes tuning hard, because I don't know the exact performance. I get this noisy one, and I have to use the field of stochastic search. Now, I can evaluate this using a simulator or in the field, but searching over it, there are two broad methods, one called derivative-based stochastic search, the other one called derivative-free. By the way, derivative-based stochastic search and derivative-free stochastic search are themselves sequential decision problems. With the stochastic gradient method, the step size alpha there, if you're familiar with this, is a decision. So you need to solve a sequential decision problem to get the tunable parameter for your sequential decision problem. So let's switch to look-ahead approximations. Now, look-ahead approximations mean you need to peek into the future. So here we have Dorothy in The Wizard of Oz, and she has to pick the best path, but she also has to think about down into the future because she needs to get to Oz. Now, here's the equation that goes behind that very simple picture. And this equation is a little frightening, but we're going to have to work our way through it. So this initial cost or contribution that's the immediate cost that I incur by making decision X, and everything else is this big messy stuff. And by the way, I have to tell you, you can't compute this. So that's what makes this thing interesting, because you can write it out mathematically, but we can't compute it. For people who are familiar with decision trees, we're going to start with, I'm at this node and I have to make one of three decisions. And so I want to make the best decision. So I want to solve an maximization problem, but after I make the decision, something random might happen. And then I go into that messy thing in the future. Now, in that messy thing in the future, at every square, I have to make a decision, and I'm going to make a decision using a method called a policy. And that policy will specify what decision do I make. And then after I make each decision, I'm going to have something random happening. Okay, deep breath. How do I get through this? So just like the policy search approach broke down into two classes of policies, this also breaks into two classes. The first of these is policies based on what are called value function approximations. So I can peel off a piece of this function to say, wow, this is some function that depends on the state st plus 1. If I could compute that exactly, and there are problems where you can do this, I have an optimal policy. I'm done. And so there's an entire fields of research based on this, but most of the time you just can't compute it. But maybe I can approximate it using machine learning methods. Now, I still have that ugly expectation. I don't like that because the expectations are hard to compute. And so I have a way of getting rid of the expectation by using something called the post-decision state variable. Now, if you come from Q-learning, if you come from computer science, you're doing something called Q-learning. What they do is they say, oh, we're just going to make this one giant function of the state and the decision. Here's a little example of where it actually works. This is for my company, Optimal Dynamics. We have drivers and loads, and as I make decisions, I have to look at decisions that are being made in the future. The question is, I need to make a decision now, and those decisions in the future involve a lot of uncertainties about what demands have been called in. But what I'm going to do is I'm going to compute a value, an approximate value of drivers in the future. And when I do this, my decision-making at time t suddenly becomes quite simple. And so I've just approximated the future. This is where you're using approximate dynamic programming. So let's imagine we have drivers and loads on Monday, and that blue rectangle is all the drivers and loads. And I have a downstream value of these drivers in the future. Now, what I can do is take an initial approximation and simulate that. Now I'm going to do it over and over again. And we do that about 15 or 20 times. And what we do, here we have actual results for about 11 different carriers at Optimal Dynamics, where we initially start at time 1, that my outperformance assume all the downstream values are 0. And then after 15 training iterations, I get improvements of about 20 to 40%. Here's an actual animation. This is a major fleet. I'm modeling every individual driver, all the details of the driver, individual loads, when they have to be picked up, which loads to be picked up, so on and so forth. I've got a lot of detail in the simulator. Now, value functions don't always work. In fact, value functions usually don't work. In my experience, I have a very small set of problems for which approximating value functions is really powerful. And the rest of the time, they just don't work. So there's a lot of people who claim they work and they're like all excited. And this is often what they mean by reinforcement learning. But in practice, it doesn't actually really work. So what do you do when it doesn't work? What you do when all else fails is you go to what's called a direct look ahead. Now, direct look ahead means we're solving that big, messy problem, but I've already admitted I can't solve it. So we're going to approximate it. So here I have states, decisions, and information, but I've got tildes on all the variables, and everything's indexed by 2 time indices. Time t is when I'm making the decision, and time t prime is me peeking into the future. Now, I have a lot of things I can approximate. I can approximate the information that comes in. I can simplify the policies. I can look a limited horizon in the future. I can throw some things out of the state variable and simplify there, and I may even simplify both the decisions and how I make decisions in the future. But let's say I can come up with an approximation that I can solve. I will peek into the future, make it optimize, figure out my decision now, roll forward, update everything, peek into the future, roll forward, do it again. And so I'm constantly rolling forward. Now, does this look like something that you would use? The answer is yes, we all use it every time we use a navigation system in the car. So here's me up in Hartford, Connecticut, trying to get back to my home in lower left-hand corner in Princeton, New Jersey. And Google Maps is telling me, hey, here's this great path right through New York City. Now, this is a look ahead. Now, Google Maps uses a deterministic look ahead. This is often referred to as model predictive control. There's an entire book on it, a whole field of model predictive control. Now, what I did was I said, well, wait a minute. I'm not going to go through New York City. There could be really terrible delays. I'll go around it because New York could be bad. That is basically plain English for what's called robust optimization. There's a long, substantial book on that. And then there's books called stochastic programming and even approximate dynamic programming, where I may not be able to solve the problem with ADP, but I may be able to use ADP as an approximate look-ahead policy. So, deep breath. I had just gone through 4 classes of policies, the 2 in the policy search strategy and the 2 in the look-ahead strategy. Now I'm going to make quite a big claim. I'm going to claim that these 4 classes of policies are universal, that they cover every possible method for making decision, everything in the literature, anything used in practice, policies that haven't even been invented yet. These are meta classes, which means as you approach a problem, you really should have your arms around all 4 classes to see which one works best for your particular problem. Let's take a little energy storage problem. And what we're going to do is, this is actual data. Here's a 24-hour period. Black is the actual energy from wind. And at midnight, I have a forecast. Now, this is real-world data. Now, every hour, I'm going to update the forecast, and we're going to see the forecast changes quite a bit. Forecasting wind, it turns out, really is hard. Now, I need to plan into the future just like Google Maps. What I'm going to do is I'm going to do it deterministically. So this is a deterministic look ahead. It's a linear program. Now, buried down in there is the wind forecast. Now, so I happen to know that that's a pretty terrible forecast. There's a lot of uncertainty there. What do I do? Because I don't want to do a stochastic look ahead. Well, one method, throw in a tunable parameter, discount it. And I'm going to do the discount depending on how far into the future. So if I look out 24 hours, I'll have 24 different factors. That means I now have a parameterized policy. Now, it's very easy to solve. It's a deterministic linear program, and I can peek forward, solve this in an eye blink, make a decision now, roll forward, solve again, roll forward, solve again. Now, I ran some simulations where I said, let's assume the forecast is perfect. I can set up my simulations where the forecasts come out true and optimize those tunable parameters. And guess what? They all came out equal to 1, just like I expect. But if you put in the uncertainty, Now I start getting optimal values of theta very different than 1. And when I do this optimizing, if I start from a base of theta equal to 1, the optimized theta gives me about a 30% improvement. Not bad. Now, optimizing the theta is not easy. Implementing in the field is easy. Now, we made up 5 different variations of this problem by playing around with the data. So we have 5 different versions, and then we came up with 5 policies, the first 4 of which came from each of the 4 classes, and the 5th one was a hybrid, similar to my look ahead with the tunable parameters. We made each one of these work best, given the data. So let's come back to our bridging between machine learning and sequential decisions. And we see we have the 4 classes of policies. The first of the 4 classes, the policy function approximation, includes every possible function you might use when you're using this machine learning. And then we have the other 3 classes. And each one of these, the policy involves solving usually a simplified optimization problem, something that's fairly easy to solve. Not always, but usually. So here we have that sequential decision problems has a lot in common with machine learning, but it's richer. And the modeling is harder, and the set of policies is much bigger. So choosing among these, this is where I get the most questions. This is a little bit of an art form. And of course, there's some intermingling because there's some mishing and mashing. In chapter 11 of my book, I have the best explanation I've been able to come up with of how do you choose among the 4 classes. There is a trade-off between how complicated the policy is to compute versus how hard it is to formulate. Now, here are our 15 books, and what we've found is there's a very strong bias in the academic community. Of these 15 books, about 10 of them are really focused, some almost exclusively, on Bellman's equation. So this is the hammer that academics like, and if they're not using Bellman's equation, well, then they're doing look-aheads, and mostly stochastic look-aheads. So these 5 books jumping out are some form of look ahead, usually stochastic look ahead. Model predictive control is usually deterministic look ahead, but then you can tune that. So now when I compare between machine learning and parameterized policies, so while the academic community has a lot of attention on Bellman's equation, when we do machine learning, we're usually saying, oh, here's a function I might look best, and now let's do some tuning to make the function work as well as it can. This is where we're tuning the parameters. There's a subset of policies in sequential decisions that are parameterized, the PFAs, the CFAs, and a deterministic direct look ahead you can parameterize. And these are behaving very much like my machine learning because I'm still fitting parameterizations so that they work as well as possible. And so, here's an example where I tune the parameters in the deterministic look ahead. See, these are the policies that absolutely the most widely used in practice. CFAs, you won't find it in the academic literature. Tuning a deterministic look ahead, again, you won't find it in the academic literature. There are sub-communities focusing on PFAs that doesn't get nearly the attention that Bellman's equation does. I think I'm ahead of the curve. This is what's mostly going to be used in practice, and it's very powerful because you can incorporate structure. Now, modeling uncertainty. This is a huge topic. Chapter 11 of my book focuses on this. I identify 12 classes of uncertainty. You could easily spend your entire career on this. It's so important that I'm not going to say anything more than 1 slide. It's a big topic. It's important. I would almost argue more important than the policies, but I don't have the time to go into this in any depth. So let me close by talking about what I'd like to see as a new educational field. In the core disciplines of decision analytics, optimization is a well-established field, a bunch of books, a bunch of courses. It's easy to hire people. Same thing true with machine learning. Oh my God, there's thousands of people graduating every year. And simulation goes back to the 1960s. It's an established field. These are established topics. You can hire people. They'll all come in. There'll be certain things that they know. But when you go to the world of sequential decision problems, it's not true. It's not standardized. The books are a complete mess. They are all using different vocabulary. They all teach you different tools. I've written a new book, came out earlier this year, Reinforcement Learning and Stochastic Optimization, a unified framework. It covers all 15 fields. It has a universal framework following what I've done before. I also have a companion book. I wrote this for an undergraduate level class, and it teaches the ideas using a teach by example style. It's not as thorough, but it focuses on just thinking about problems the right way. And I claim that these two books are an initial foundation. We can start teaching this material inside universities, and I think it's time. So I'd like to thank everybody. I have a number of links, but if you're only going to remember one link, remember just that last one, tinyurl.com SDA links. That is a web page that has all the other links on it. There's a lot of resource material, books and videos, and just web pages with other educational material. Thank you, everyone.
Thank you, Professor Powell, for an excellent talk. It was very enlightening, lots to take in, lots to absorb. You really, you talked about sort of the zoo of the jungle, if you will, of the various approaches, and you took us through a very lovely safari to help us sort of make sense of what's where. So a couple of questions come to mind, if I may. So the first question that comes up is, in your framework, you referred to an entity called belief, and you mentioned sort of on some slides the stochastic nature of some of the transition functions. You also then mentioned the idea of partial observability of the state, or sort of incomplete information about the state. Would you say that this belief entity is useful for modeling, accounting for the partial observability, the stochasticity of the transition function, or both?
Well, so it's for any time that you have a quantity parameter you don't know perfectly. So, for example, partial observability, like if you don't know what's going on inside a patient, or if you don't know what the inventory is, or you don't know what's going on in climate, and you have uncertainties, you've collected some data, you have at best a statistical estimate, that goes in a belief state, okay? And the way that evolves is using classical either frequentist or Bayesian statistics. By the way, it's not all Bayesian. It can easily be frequentist, but the standard statistical updating. And so this is where there is a true parameter that you don't know, but there's a probability distribution. Use whatever probability model that you would like. Now, when you have stochastics, do you always have a belief state? And the answer is no, but I'm guessing in most practical problems you do. And the belief state is probably one of the most poorly understood concepts in stochastic modeling. There's an entire field called multi-arm bandit problems that only have a belief state, where I have let's say a set of drugs, and I only have a belief about how well the drug will perform. And so you only have a belief state. And then there's problems like optimizing trucks around, where I just have the stochastics and the trucks and whatnot without any beliefs. I think there's many problems where once you understand a belief state, you start realizing, oh, wow, that would be a useful thing to put in. Because once you put in and start thinking about it, you realize I can start making decisions that allow me to collect information. Like I'll try that higher or lower price for a product and see how people respond. So I learn. So you start realizing you can make decisions just to collect information, or at a minimum, you realize you do something because you might learn from it.
Fantastic. That's great, Professor Powell. That's very clear. Another question that comes to mind is, in the framework, you talked about sort of this variable C referring to cost or contribution. Now, in terms of actually software support and putting this into a mathematical solving or some kind of a package to do this kind of modeling, would you say that the better way to sort of represent this C is some kind of a computed or a calculated value that is given as sort of one as a scalar, for instance? Or are you saying that it's a better way to do it if it's a vector that contains all the possible 0 to n costs and 0 to n contributions to be solved? Okay, so if we're going to use the computer has to say, here's one decision, here's another decision, which one's best? Okay, so the computer desperately wants one number. You go into real world problems with any complexity at all, and you have multiple metrics. You may have costs and profits and customer service. Most real world complex problems have more than one metric. So there's two ways to pull different metrics together. One is to do a weighted sum, to put weights on them. Another is to put certain metrics, maybe weighted in the objective function, and then have other metrics to say, I don't need to maximize or minimize that metric, but let's say I'm covering demand. I want to cover demand 97% of the time. I have just decided that's the right number, So optimize your profits, but cover 97% of demand. And so the demand coverage metric is in there as a constraint rather than an objective. But if you want to have computers helping you, a computer needs a single number that says, oh, here's the metric for this decision. Here's the metric for this decision.
A is better than B. Okay, we'll go with A.
Perfect. Thank you. Thank you, Professor Powell. That's great. And the last question that comes to mind is for researchers and scholars in the field that are looking to explore this notion of sequential decision analytics further. What would you say are you talked about some of the open research challenges, but what would you encourage some of the new students and some of the upcoming researchers? What areas would you say they need to look at in this domain?
Well, let me just make a comment. My last semester at Princeton, I had 27 grads, undergrads, postdocs, and over $1 million in funding. I never ran out of things to do. Belief states are a biggie. Okay, there's very, very little work combining physical states and belief states. Big community out there with belief states for multi-armed bandit problems, but that's broken into different communities. But when you combine, let's say, a drone that's going to be moving around, think Ukraine, or think of a drone moving around a wildfire, where the drone has to collect information that guides, say, a helicopter dumping fire retardant on the fire. So you have an information collection decision and an implementation decision. Very little research on that. There's a lot of stuff on, chapter 20 of my book is on multi-agent systems. Now, there's a massive, massive literature on multi-agent problems, but it's been done without my framework. And generally, if you go in, the modeling is very poor and the policies are often just sort of trivial. Now, in a multi-agent setting, you may have things like, well, what's an agent? Maybe it's a drone. Maybe it's flying around. It doesn't have a lot of energy. It doesn't have a big computer. So you have these various computing constraints. So if you go into the world of robotics and multi-agent systems, you're going to find a massive literature. And then if you open up the papers, you're going to find the modeling is very poor and the policies aren't very sophisticated. And then there's still challenges on how to make these things work together. I've got a student working right now on a problem. It sounds really simple. We have to optimize a function, a scalar function. The problem is the function is very noisy and very random. So I can maybe do 5, 6, 7, 8 observations, and I get very noisy observations, and I still want to optimize it. How do you do that? This happens a lot. I've met somebody who had 3,000 compounds that they had to test, and they had a budget to test 30 of them. How do you find the best out of 3,000 compounds when your budget will only allow you to test 30? Well, it turns out it's through the belief models, because there's a lot of correlations. Testing one compound teaches you about others. Let me tell you, when I had the 25 students working with me in that last thing, I had no trouble coming up with topics for each of them. Because when you blend the complex decisions with the uncertainties, and especially with the beliefs, oh gosh, there's so much to do there, because the academic community just hasn't done very much. I have found I don't have any trouble. Tell me a student who wants to come in with really strong math background, who wants to do something advanced and prove theorems, no shortage of things to do. But they're also very practical. But now you take a more applied student. The beautiful thing about this framework, it's very, very friendly to an application-oriented student, because you can take virtually any physical problem and map it to this vocabulary. I claim that if you never read anything that I've written, and you sit down and just do some hack job writing up code, I can take your code and map it back to my notation. There's a one-to-one relationship between my mathematical modeling and code. And because my 4 classes of policy are universal, if you just do some hack job on how you make decisions, it still fits in my framework. I probably can then tell you, oh, and I have a path to how to make it better. Because a lot of people will just do something hack and not realize that they either have a tunable parameter or could have. And then the tuning process is hard. Let me tell you one big problem. How do you tune parameters? Do you tune it? Most of us will say, well, of course you do it in a simulator. The real world often doesn't have either the time to do a simulator, or sometimes you just can't simulate some processes. I can't simulate what's inside a human body or how the market will respond. I cannot use a computer to find an optimal price. And so how do you do learning in the field when experiments are very slow and very noisy? Boy, do we need more research on online learning.
Absolutely. Professor Powell, this was excellent. And thank you so much for sharing your insight and foresight with our community. And what a thoughtful and thought-provoking conversation. So I know this is such a rich field. We'd love to have you back in a couple of months and continue to share your wisdom with us. But on behalf of the Synthetic Intelligence Forum, I'd like to sincerely say thank you.
Thank you. And thanks to everyone.